All right, guys, more on statistics. Let's let me see what I'm doing here. Okay, first of all, first of all, I define statistics as the science of collecting, analyzing, and interpreting data. It has two branches, as we've talked about before: descriptive statistics, describing raw data in the form of graphical representations and numerical summaries. We've looked at some of that with the graphical summaries as box plots and histograms and pie charts, and our numerical summaries, means and standard deviations and medians and frequencies and percentages and so on. Inferential statistics is inferring or estimating population parameters from sample data. A little bit more on that, a population, just in case it's been a while since you've had your last statistics class, is a complete set of people, objects, things, trees, cats, cars, whatever it may be that we're studying. And measurements from a population are called a parameter. A sample is a subset of the population, and in research we seek a random sample. So measurements from a sample are called a statistic. So I think this is where statistics kind of gets challenging for a lot of people because, for example, when we say a mean, an average, well, we have a population mean for everyone and we have a sample mean for our sample. Well, usually the sample mean is unknown, or well, we may kind of have an educated guess about the value and we want to test it. But usually the population value is unknown, and we use a sample to test a claim about that value or to estimate it. Speaking of two components of inference, number one is called a confidence interval. This is where we use our sample data to make an estimate of an unknown population parameter based on a certain level of margin of error. And hypothesis testing is we use sample data to test a claim about an unknown population parameter value. Significance. Now, significance is something that comes up a lot in carrying out a test of hypothesis. And again, a test of hypothesis is just one of the procedures under the heading of inferential statistics. So just to give you kind of a, where we are on the timeline, even though we're going to review this, I'm pretty much done with descriptive statistics. We are now moving into inferential statistics. Okay, so the parts of hypothesis testing state the null and alternative hypothesis. We'll talk about that a little bit more. The level of significance. Guys, usually it's 0.05. In fact, in research, you rarely see your level of significance anything other than 0.05. You calculate your test statistic and p-value. We'll use technology to do that, make your decision on your null hypothesis, and write up a brief summary. The significance of our test: if we reject the null hypothesis, then our test result is significant. And if we fail to reject the null hypothesis, then our test result is not significant. Significance is established by comparing our p-value with our alpha. So if our p-value, which we'll use r to calculate the p-value, is less than alpha, then we reject the null hypothesis and we have statistical significance. If the p-value is greater than alpha, then we fail to reject the null hypothesis and we do not have statistical significance. So, p-value less than alpha, p-value less than 0.05, statistical significance. P-value greater than or equal to alpha, we do not have statistical significance. So what's a p-value? I just saw a study about an hour ago that said something to the effect that 52%, I believe it was, or 50-some percent of graduate students couldn't properly define a p-value. The reason they can't is the definition really isn't as important as knowing to compare it to alpha and make your ultimate decision about your test result. But nevertheless, it's kind of cool to understand what this thing is. So the definition of a p-value is if we assume the null hypothesis to be true, and that's the whole dynamics of a test of hypothesis. We assume that this distribution of scores exists with the parameter value that we're testing. And if we get something very close to that value, then there's no reason to think that that value is not right. So we fail to reject the null. But if we get something a long way from that value, then it's kind of more reasonable to think, well, did we just have a bad day and get a weird sample, or are we truly drawing from a different distribution with a different parameter value than what is being hypothesized? So guys, a p-value, assuming the null hypothesis is true, a p-value is the probability of seeing data like the one we got, or even more extreme. Now, this is where, as a statistician, this brief approach to that I'm doing in this class kind of drives me crazy, because to thoroughly understand a p-value and probability, we would need to go through about 3 or 4 weeks of normal distributions and sampling distributions and probability, binomial, lots of different things. So it's just one of those things that I guess for this component that I'm teaching you guys, if we could just understand that when the p-value is less than alpha, we have statistical significance, and when the p-value is greater than or equal to alpha, we do not have statistical significance, I'm okay. Anything else, and you can always Google p-value if you're really interested. All right, let's look at a really, really basic example of where a test of hypothesis would possibly be appropriate. So guys, I've been to Shawnee now for 24 years. I've driven from my home to the SSU campus many times. And I'm convinced on average that my commute time is about 90 minutes. Some days I make it faster. Some days it takes me longer. A friend tries to convince me there's a faster route. I intend to test his claim that his route is faster than mine. So although it may be tempting to take the friend's route once and generalize, that's not the way statistics works. We need variation in our sample. So I would set out to drive this route 10, 12, 15, 30, 100 times, whatever. And then I would carry out the test of hypothesis based on the sample data that I've collected. So again, that final sentence right there is so important. We need a sample in order to have variation among our measurements. One thing you learn about statistics as you get higher and higher is when people walk into my classes, the introductory level class, the first day, and they think, oh, what do you know about statistics? Well, I know how to get the average. I can even do a median. They always tell me a measure of central tendency. But as you get into statistics more and more, especially when you come to the level that I am, you understand the statistics. It's all about variation. It's not really about as much about the measure of central tendency as it is the level of variation. So guys, back to the example of the driving time. The null hypothesis here would be that the mean time is 90 minutes. And the alternative hypothesis is the mean time is less than 90 minutes. As always, set my level of significance at 0.05. And, is it always 0.05? Well, I could literally teach a 3-hour course just on level of significance. It's that complicated. We get into type 1, type 2 errors, we get into power, effect size. You get into all these different things that at the end of the day really affect your level of significance. Let's keep it simple, as most researchers do. Let's set alpha equal 0.05 and go on with our business. Third bullet there, I'm going to drive the route. Is it route or route? Route, I think. I'm from Kentucky. We screw up everything with the English language. So we drive the route a set number of times and analyze the sample data in R. So our focus will be on 3 things: our test statistic, our p-value, and our confidence interval. Well, guys, just so happens that in R, I have entered some times. Now, don't take this literally because I just made this up. Uh, I don't know of a faster time. I don't have a friend that suggested a faster time. I'm just using this as an example to get the ball rolling for what we'll do next week in class when I actually come to your class and we work on some things. All right, so I'm going to hit enter, and so I now have my data entered as time. Now, I could have gone into an Excel spreadsheet and typed these numbers into a column and saved it as a .csv and gone through the whole set your working directory. But with a smaller data set, I find this easier. Plus, guys, you have to use what's called the C function. You can't just type the numbers in. So, just like before, I'd probably want to look at the mean. So the mean is 86.7. That's quicker. That's about 2.5 minutes quicker. But again, it's not only about the mean, it's about the variation. Standard deviation of times, 4.40 rounded to 2 places. I can do the quantile of time. And I can get, my quickest time was 81 minutes. My longest time was 95 minutes. But, if I want to, we can see if there are any outliers. There's not. So you can see the median right here comes over to about 87, and the highest number and the lowest number. This horizontal bar right here is the value for Q1. So that's around 82.5, and this looks like it's about 88.5. Might want to look at a histogram. I don't know. Why not? And have a little bit of right skewed going on because we have a lot of measurements. 4 measurements. Let's see if I can go down and get that. Yeah. So looks like from between. This is 85, so this is probably about 82, 84. Yeah. So between 80 and 82, it looks like there's 4 measures. In 82 to 84, there's 1. And histogram, fairly symmetric, but has a little bit of right skewed to it. Well, guys, now what I'm going to do is I'm going to carry out the test and see whether I should take this person's advice. I'm going to do what's called a t-test, and I'm going to use times, and I'm going to set mu equal to 90, and I want a alternative equal greater. Now, how would you know? Typically, how would you know to type this stuff? Typically, you learn it from a professor, whoever you're taking your statistics class from. But R is so popular these days that there's all kinds of documents out there that help you decide the code to run, dependent on the test that you're trying to conduct. So don't be afraid to Google it. If you want to Google confidence interval for mean, just say confidence interval mean and then put a capital R, and you'll get about 1.8 million hits of stuff that could be helpful. So when I get this, guys, I have, no, that shouldn't be greater than. I don't want to take what am I thinking about? I don't want to take a faster route. I want to see if it's, I'm sorry, I don't want to take a slower route. I want to take if it's a faster route. So guys, I have, when I look at this, I have tunnel vision on one thing. All this other stuff is interesting. But guys, I have tunnel vision on one thing, and most researchers do. Do I have significance? And my p-value is less than 0.05, which indicates to me that we should reject the null, that the mean is 90 minutes, in favor of the alternative statement, which is the mean is less than 90 minutes. Now, if this p-value had been 0.05 or higher, then I would have failed to reject the null, and the evidence would support the statement that the new route is also 90 minutes, so it doesn't save me any time. To get the confidence interval, okay, this is your test statistic. This tells me that my sample data is 2.876 standard errors. below the claim that the mean time is 90 minutes. And then to get a confidence interval, it's one thing I really don't like about R. To calculate a confidence interval, you have to get rid of the alternative. So if you're doing what's called a one-tailed test where your alternative hypothesis is less than or greater than, your 95% confidence interval will be irrelevant. You have to run a two-tailed test to get a 95% confidence interval that's useful. So I would have to get rid of the alternative and just run a two-tailed test. And I can see there's a 0.95 probability that the mean time, again, we're not just talking 15 times here. I'm talking about if I drive this every day for the rest of my life, my population as it would, as you can think of it. There's a 0.95 probability the average time in this new route would be somewhere between 84.3 minutes and 86.2 minutes. Now, obviously, there's kind of a common sense component to this. It may be quicker, but it may be more dangerous. It may have more variation. Maybe I'm just more comfortable. So, just because you get statistical significance doesn't mean that you necessarily throw the baby out the bathwater and forget all that you already know. This time is statistically significant faster than the time I'm taking based on this fictional data set that I've created. And I set out to get a p-value less than 0.05, so there's that. All right, gang, we got some good stuff in store. We're going to go from t-test to two-sample t-test. We'll get into some ANOVA. We'll go into some multiple regression, linear regression. I'll probably even give you a short segment on logistic regression. That's actually what my PhD was about, so I like to think I know a little bit about that one. But we're going to have some fun, all right? Or at least I hope we do. All right, take care.